I'm covered. Okay, there we go. That's better. Hey everybody, how are you? Long time no see. No, I think we just finished our previous workshop only a couple hours ago. And me and Ryan Lay, we've been trading spots today. So you all haven't gotten any rest, have you? Let's see if there's any comments here. Can you all hear me okay? Just let me know in the comments if you can't hear me all right. But yeah, just let me know. And while we're waiting to get some feedback there, oh, defendant, hey, how are you? Good to see you again. While we're waiting to get some comments here, I want to just send the check-in link because it's really important to get that going for all of you. Oh yeah, just doing well. Happy to be here for another stream. And yeah, Global Hack Week's almost coming to an end, so I'm kind of sad about that, but otherwise, doing pretty good. So yeah, why don't we go ahead and share these slides? Gonna upload them. So I saw that you all voted on what we should cover. And let me share my screen to show you that. So last time we covered, you can see there was responses. We covered the classification. So we did vision transformers. And actually, why don't I show you all the results of my training, huh? Because I did promise to show you what it looks like when the whole thing is trained. Did anybody get their model to be fully trained? Anyone at all? It does probably require, to get it done in this amount of time, you probably did need to have a subscription. But yeah, here was the result from last time. And you can tell that there were 10 epochs, and the loss went down quite a bit in the training. In the validation, less so. Looks like, honestly, our validation never really got that much better. But you can see the characteristic curve of the training data set here. So the loss went down as we got more and more epochs. Interestingly, the validation loss, if anything, you could maybe make the argument that the loss went up over time. And what that might indicate is a little bit of overfitting, because we would definitely expect it to at least stay the same and maybe go down with the training data. Because yeah, if you see, the accuracy is actually going kind of down, but mostly just staying stagnant. So this would be maybe an example of overfitting. And what you could do to try and solve that is you could look at the learning rate parameter. So you could potentially increase this learning rate parameter so that it arrives at a solution much faster and maybe reduce the overfitting. The other thing you could try to do would be to reduce the number of epochs, because we did have quite a few epochs. You could decrease the batch size also. Decreasing the batch size would make the data see less, or make the model see less data every batch. So, but regardless, we got quite a good result, about 95% plus accuracy. So yeah, hopefully you all are able to see that. Maybe you'll have to go to sleep and wake up in the morning and try it. But we did have a couple of other results here, which were to do linear regression and wildfire. So I think what that means is I'm gonna probably do both of those. And maybe we'll start with the wildfire example, and then we'll do linear regression. So the wildfire example was a reinforcement process. And if you don't remember from the slides, reinforcement is one of the major classes of machine learning algorithm. So I'm going to talk about one in particular called the Markov decision process algorithm. And we will sort of walk through, and we'll even do an example in Python. All right, so just to tell you a little bit about the Markov decision process, it is a reinforcement learning algorithm that is designing a policy to fit a scenario. And it has four main components to this scenario. The first is the states. So these are the possible states that the data could be in. And then the second one is the transitions. So the transitions indicates from what states can change to. So you could maybe have, let's see, what would be a good example? Okay, so you as a person, you can transition from being a baby to being a toddler, and from toddler to teenager. But you cannot transition from being a toddler to a senior citizen, right? That's impossible. You have to go through the other steps first. So those are just some transition examples. And then actions are like what you can do. So what your algorithm is capable of the way it's capable of acting. And then the outcomes are what come at the end. So it's kind of almost like a video game where you could have these possibilities. And so here's an example of a scenario. Okay, this is a travel scenario. And has anybody here ever been to either of these cities, San Francisco, California, and Los Angeles, California? I'll tell you, right now, I am sitting in one of these two cities. If you can guess which one, I'll give you extra point. I don't know what an extra point will do, but yeah, let me know if you've ever been to one of these two cities. But they are in California, and oh, what is LA? Good guess, Robert Taylor. That's right. I'm here in LA. So nice. You get an extra point for you. But yeah, so these two cities are, about 6 hours away by car. by train, they're 11 hours away. Amazing how bad our trains are in California, our long haul trains. We're trying to build actually a 4.5 hour train from San Francisco to LA. So wish us luck on that. It's been about 20 years since they started that project, and I think they're trying to get something done by the Olympics, but I don't think it will realistically happen. And then someone else, a defendant, says, I've been to San Francisco. That's awesome. Yeah, it's a great city too. But then plane ride is actually probably the most common way to travel between the two cities, and that's a 1.5 hour plane ride. So, if I were to ask you which of these routes will get me to Los Angeles fastest, you would probably say the plane, right? I think most people would. And you'd be right, because that would just optimize based on the time. So we're just taking time as our cost function in machine learning. We call that cost function, and we minimize it. But let me give you another example, and I want you all to solve this on your own. Imagine that the car ride has a 10% chance of severe traffic. So 1 hour of possible traffic, and that would bring the ride up to 7 hours, not 6 hours. My goodness, could you imagine being in the car for 7 hours? It's brutal. I've done it before. It's no good. But sometimes you got to do it. And then here's another complication that I'll add to it. Okay, I'm going to add some complications to your plane ride. Let's say there's a 10% chance that you get delayed in security. That's 2 hour delay. And let's say there's a 25% chance of a plane delay. So that means that the plane was delayed in addition to your security delay, adding another 3 hours. And then there's a 5% chance of a deplane delay. So this is when the plane gets to the airport, but they have trouble getting the passengers off on time. In this case, I want you to tell me which of these two will be faster. Does anybody want to guess? On average, well, let's say of these three, which one would be fastest? Let's try to do the math together. So the car takes 6 hours. There's a 10% chance of severe traffic. So we'll say 0.1, probability of 0.1. And then you multiply that by 1 hour. And it yields 6.1 hours. All right. So this is the car trip. But the plane is a little more complicated because we have a lot of things that could happen to us. So let's say for the plane, it will be the average plane trip. It will take 1.5 hours plus there's a 10% chance of an extra 2, a 25% chance of an extra 3, and a 5% chance of an extra 1. So in total, let's see, 1.75, and then you add another 0.75. So it's 2.5 hours of travel. So because the average plane trip was less, we would choose that, right? Even though there's so many possibilities for delays, it's just so much faster to take the plane. And by the way, the chance that all three of these will happen to you is pretty low, right? I mean, it's probably a less than 1% chance that all three of these delays will happen to you in the same trip. So 2.5 hour plane ride. Okay, and let's now complicate things. So here we're going to say, I want you to get there as fast as possible, but I also want to get to LA in 8 hours or less. And I've actually changed the deplane delay so that it's actually 1.1 hours, okay? And the security delay is 2.5 hours. The chance of the plane delay is 3 hours, okay? So now, based on these new numbers, and the fact that we need to get to LA in 8 hours or less, what would be the best choice for us? Does anybody know? All right, so I'll give you a hint here. Imagine that I were to tell you that the answer was the car. So you take 6 hours and 10% chance. So defendant says it would be the plane. So let's see. If we add up all of the hours in the plane, if we do get a security delay and we get a plane delay and we get a deplane delay, that will be equal to, let's see, 2.5 plus 3 is 5.5 plus 1.5 is 7, and then plus 1.1 is 8.1. So that's actually the plane. If you get all the delays, you're really going to push it to 8 hours and above. So you're going to push that limit. So even though the plane will almost always get you there faster, it's going to be a little too long in the worst case scenario. And so you might think, oh, the car, right? Well, the worst case scenario for the car is 6 plus 1, which is 7. So that's going to get you there in 7 hours. But actually, the answer is that you will want to go to the airport first and then wait there for an hour. If you get through security fast enough, then it means that no matter how delayed the rest of your trip is, you will get there within 8 hours. But if you're in security still after 1 hour, you're at the airport after 1 hour and you still haven't left, then you definitely have to go home, grab your car, and start to drive, because that is the only way to guarantee that you're home, that you're to LA in 8 hours. All right. So this is the optimal strategy. It's to go to the airport and then wait there for 1 hour. And then if you are not able to pass through security, get in the car and drive to LA. So it's a little bit counterintuitive, actually, some of these. And we're going to explore the concept behind it a little bit more in detail. This is why we might need some machine learning techniques. So we can define all of these as states. So for example, San Francisco could be state 0. The car Driving in the car, choosing to get in the car and drive would be a transition from state 0 to state 1. So you've just done the car. It's possible then you hit some severe traffic, so you would transition into state 2. Or you could just get straight to LA and go to state 7. All right. And then there's another possibility, of course, which is that San Francisco, you transition into the train, you get into the train, and then you get to LA. Nobody wants to take the train. I don't know many people that ever take the train to go between these two cities. But it's possible. And then here is the plane. So you go from state 0 to 3, 4, 5, 7. Going through security, going through all these different things. And we just label them with S sub n to indicate those states that you can be in. And so we can then create a state transition matrix, which describes the probability that a state will transition into another. So for example, P12, you can see it's in the row number 1, because the first row would be row 0. So this is row number 1. And then the column is actually column 2, right? Because it goes from 0 to 1 to 2. And then that probability is the probability that state 1 will transition into state 2. So when we look at state 1 and state 2, it's that chance that the car will encounter severe traffic. And so that would be 0.1 probability. All right. But let's calculate that out for each state. And then the rewards matrix is another thing in this Markov decision process algorithm. It calculates the reward for each action combined with the current state. So this is going to be that outcome portion of the scenario. So the reward for starting from San Francisco, state 0, and choosing the train, state 6, is 11 hours. And in this example, it's a little counterintuitive. We actually want to minimize our reward or our time taken. So that's a little counterintuitive, but that's just sort of how it works with this algorithm. And so here is an example using social good. So we can just kind of think about ways to use our algorithms for benefit. And it's going to be in forest management. So forest management is a way that people can make sure the forest grows appropriately and does never really causes an environmental hazard, but it also can yield lots of lumber for building homes, for paper and doing paper products, things like that. So forest management would be a good example. And we want to make sure that the forest is allowed to grow, but that we can get the lumber too. So here's a state diagram for our forest. And in this forest, okay, there are 3 possibilities. There's a new forest, which is state 0. And then there's also a middle-aged forest, which is you could call state 1. And then there's a mature forest, which is state 2. So in each state, there's a possibility to transition to the next one, which we would just describe as growing, right? So our little sapling becomes a mid-sized sapling, and then that mid-sized sapling becomes a very old tree. But at each step, it's possible that these trees will burn into a fire and the whole forest will start back from a new forest. So there's always that 10% chance that a wildfire will come through. And actually, just to show you how big of a problem this is in this area, this San Francisco to LA area, I'll show you what we're dealing with right now in California. These are the current emergency incidents. You can see ongoing ones. There's, hundreds literally of fires. And here's the currently active incidents. So there's a mountain fire and eternal fire. But yeah, you can just see all of these fires that happen along the journey from San Francisco to Los Angeles. Look at this. There's even it seems like there's a helicopter over here. I guess it's on its way to fight some fire. But yeah, so let's build our rewards matrix now, because we've done our probabilities and our state transitions. So our rewards matrix, we will give a reward in order to cut the forest. And so in the new forest case, to cut the forest would be a reward of 0, because there's, of course, no wood that you would get from that new forest. And then in our state 1, our middle-aged forest, that would be $1. And then in state 2, there's $2, let's just say, because by the time the mature forest is there, that's great. We can get a lot of wood from that. All right. And Sandra says, can you share the slides? Absolutely. Hi there. Yeah, no problem to send the slides along. And so there they are. They're just in the chat now, so you all can see. But there's another choice that we have in order to manage our forest. We can choose to keep the plant and not cut it down. And of course, the amount of lumber we can get from the tree is 0 every time that we keep it, right? But in this case, I'm saying that there is a reward for allowing the mature forest to stay. And that's because we might have some environmental law in the state or in the country where when you keep your tree and you don't cut it down, the state will give you some nice benefit because it will be there. Oh, someone says, can you share the slides for part 1 too? Sure. Yeah, I can share the slides for part 1. Let me share that. There it is. Slide 1. So now you can check those. Yeah, thanks for reminding me about that, Sandra. That way everyone can take a look at that. But yeah, so our keep option would just be 004, right? Because they won't necessarily reward us unless we have a nice mature forest that the critters can use and the people can look at and things like that. Okay, and I have a 10-minute break here, but I'm actually not going to give a break. But if you need a break, please pause at any time because we do have a recording of the whole workshop. And we have too much things to cover today to take a break. So because we have to do our Markov decision process, and then we're going to move on to linear regression. So yeah, why don't we take a look at this MDP toolbox? I'm going to navigate to the tab in my browser. And, oh, it's not very easy to see that. Let's see if it's any better. There it is. That's a little bit better for all of you, I think, to see. But Yeah, we have this great toolbox provided by this Python developer, um, the MDP toolbox, and it provides a bunch of classes and functions for the resolution of the discrete time Markov decision processes algorithm. So there's several modules in here. The way we import is to import MDP toolbox, and we're going to do MDP toolbox.example. We're going to import this wild forest example. But yeah, actually, let's take a look at this example. And so this is one of our examples, actually, forest management. So we're going to take a look at that by loading it. Let's take a look at the documentation here. So MDP toolbox.example.forest creates the MDP example based on this simple forest management scenario. And S equals 3, it is the default argument for the state, the number of states. So we're just going to give, again, very young tree, middle-aged tree, and then mature tree. Those will be our 3 states. But you could, of course, play with that and add some more states if you want to for your forest. And then R1 equals 4. So that's that reward I was telling you about that the government will give to the forest manager for keeping the tree alive for environmental benefits. So we'll do R equals 4 for that. And then R2 equals 2. So this is going to be that benefit that the forest manager gets from chopping down the tree. Okay, so that might be some lumber benefit. And then P equals 0.1, that's the probability of wildfire. Okay, so each year there is a probability, P, that a fire burns in the forest and all of the trees go back to state 0. Okay, and so we have some of these states below, and you can see, you know, how the probability transition matrix is applied. And so there's P0. P0 would be the state transition probabilities from that new forest. So there's, of course, some probability that the new forest will not become older. And that's 0, 0. So it just stays young. And the reason that could happen is because of a wildfire. So that's why the probability is indicated by P here for that. And then here we have 1 minus P, which is the probability that the forest will be allowed to grow the next year. So that's a 90% chance that state 0 will transition into state 1. So that new forest will become a middle-aged forest. And then over here, you have 0. So the reason we have 0 here is because, of course, the new forest cannot transition into a mature forest in 1 year. That's impossible. Just like it's impossible for a child to become an adult in 1 year. Impossible. Unless you're 18, then you're technically possible, but kind of not too. So yeah, we put 0 for that one. And then in the next row here, you can see that this would be the probability that the middle-aged forest would transition into the older forest. So yeah, and then here is the one for the mature forest. So you would just see 1. right? And then, oh, actually, excuse me. This would be 0. So this is for if you don't cut down the trees. So these are all the transitions that would happen. And then in this case, it's P1. So this is if you do cut down the trees. This is the probability state transition matrix. So all of the states would just return to this new forest, right? Because that's what happens when you cut down the forest. There's a 100% chance that they would all go back to that new forest case. Okay, so then let's look at the reward matrix. And remember that if we do keep the forest, if we do cut the forest, right? So that's that R1. But if we keep the forest R0, there's no reward until the very end. So at the very end, we get R1. That would be $4 for keeping the trees alive. But then R1, this case where we cut, the new tree is $0, but every other tree would give 1 until the most mature tree, which gives $2. So we can check those out. And yeah, of course, these are all of the arguments that we could change, but I'm just going to keep the example going for now. So let's stop sharing here, and I'm going to actually send you all a code, which is going to be our code for this workshop. It's a Python notebook on GitHub that you can just download. And we're going to look at how this looks in Python. So I'm going to download the raw file, and we'll build it in our coding Scratchpad together. Okay, so the first thing we're going to do is install PyMDP Toolbox, which is that Markov decision process toolbox. And you just use the exclamation point to do that. And oh, it actually seems like the this might be a bit of an old. Oh, never mind. The it works. This code. Okay, so let's just keep going now that we have it installed. And so we'll do an import statement to import. We're going to import MDP toolbox as .mdp. That's going to give us our solver and things like that to solve the algorithm. And then we'll also import MDP toolbox.example. And we'll import NumPy because NumPy is very useful. Okay, and so trees can be either young, middle-aged, or old. So we actually have that from our example. You guys can see on the notebook that I linked that there's a little description, but I'll just copy and paste it in to the notebook here so that we can all look at it together. Make it a little bit nicer for you all. Yeah, so trees can be either young, middle-aged, or old, as we mentioned, 0, 1, or 2. And each year the trees get one stage older. But there's also a 10% chance that the forest burns down, and you would just get nothing, honestly, if the forest burns down. But if you cut them down, and then you'll get 0 points for a young one, 1 point for a middle-aged one, and 2 points for an old one. So the best strategy we'll then just check out now. So let's talk about the inputs into this algorithm. Okay, so I'm just going to make a little comment here. So one of the inputs is S, which is the number of states. In this example, 3. And then R1, remember we saw this from the documentation, it's the reward that you get for waiting. From the oldest trees. R2 is the reward for cutting the oldest tree. And then P, finally, is the probability of a wildfire. So this is really the risk, right, that you would get nothing. And then I'm going to use some, I want some output. So I want to get the P, which is the transition probability matrix, which is a NumPy array of shape A, S, S. And so A is the possible actions make a new line. A is the possible actions, and S is the possible states, okay? So that's P. And then R will be the reward matrix, which is a NumPy array of shape S, A. Okay, so that would be our reward matrix. And so let's actually create these. So I'm just going to say P and R for our variables that we want to return in this function. And then we will say that it's equal to MDP toolbox.example.forest, just like we looked at in the documentation. And the keyword arguments we'll pass in are S equals 3, R equals 4, R2 equals 2, and P equals 0.1. All right, so we run that, and if we were to explore the probability transition matrix, we'll just print out P. So this is what we get. It looks just like what we got for the exam, for what we were describing earlier. And so let's check out P0. We can say this is the probability, I'm going to just say PTM, probability transition matrix, if we choose to wait. So if we choose to wait, we should see these probabilities where there's possibility of wildfire the next year, but mostly things will grow like normal. And here is the PTM if we choose to cut. That's P1. That gives us 1, 0, 0. So I want to now ask the question, what is the probability that a forest in its youngest state will advance to the next oldest if we wait? And so the way that we calculate this is we say we're going to wait, so we say P0, and we know that the forest is currently in its youngest state, so we just type another 0. But it may advance to the next oldest, which is 1. All right. So if we run that, we get 0.9. And that's 90% chance that it'll go to the next one, which is what we expect. And then what's the probability that a forest in its oldest state will burn down if we wait? That's the next question. And we would use P020 because, again, we choose to wait, so that first index is 0. The forest is currently in its oldest state, so we choose 2. And burn down means that we would go to 0. So, that state is going to just go back to the very youngest. And so we run this and we see that we get 0.1. So that's the probability that a forest fire happens, right? So now I want to explore the rewards matrix. So the rewards matrix has a shape of S rows and A columns. So S would be the state, and A would be the actions that you could take for that reward. So let's go ahead and investigate this a little bit. I'll just type R underneath so we can see. And you see the rewards matrix looks a lot, it looks a lot smaller than the P matrix. And it's really only showing us 2 possibilities. There's the first column, which is the first action, that action of waiting, 004, and the second one, which is 012. And so let's ask a question. What reward do we get if we choose to wait? So remember, wait is that 0 column. And the forest is in its oldest state, which would be the forest is in the oldest state. So we actually want to do the following. We want to do r.t, which transposes the matrix, and then we'll type 0, which gives us the rewards. And remember, the forest itself is in its oldest state. So this is the rewards vector. I'll just say rewards vector. And then this is the oldest forest, let's call it the forest state. So the forest state is currently 001 because the forest is currently in the oldest, which is state 2, S2. So what we want to do is multiply the rewards vector by the forest state and then sum them. So if we just multiply them, we see that the reward is 4, and then we do sum. So our reward is $4 for saving the forest. So that checks out. And if we were to choose to wait, and the forest is in any other state, okay? So let's just copy this, paste it here. We have 2 possibilities. I'll print them out separately. But we essentially have 2 possibilities. There could be the forest in the middle state or the forest in the youngest state. But in either case, remember, we're not choosing to wait. We're actually, we're choosing to wait still. But what if we choose to cut, right? If we choose to cut, then this first case would give us $1, but the second one would give us 0. So those are just some ideas for how this would work. And now I'm going to talk about finding the optimal policy. So this is where we will choose what is going to get us the most money over time. So we can just look at what we would call Q-learning, which is a method of optimizing the Markov decision process algorithm. Okay, So let me get back to my Visual Studio Code. I lost it for a minute there. So we say model equals MDP toolbox dot MDP. You see, it's already suggesting I use finite horizon. I prefer Q-learning, which is a reinforcement learning method. And we'll give it the following. So we give P, which is, of course, our probability transition matrix. We give R, which is our rewards matrix. And, excuse me, we'll give a discount rate. And you all might not be familiar with the discount rate, but the discount rate tells us how likely it is that the current probability transition matrix and rewards matrix setup will persist in the future. So if this matrix is likely to change, so for example, let's say you live in a country where the government is always changing the policy about forest management. Well, if you do, then you want to issue a high discount rate, because that would mean that you might want to cut all your trees down right now, because who knows if they'll keep giving you $4, for example, to save the trees. But right now I have it set to a pretty low discount rate, and that's because we're just going to assume that this policy will stay pretty consistent. Oh, sorry. So actually, it's the opposite. So 0.1 would be a very low discount rate. So it means that we're pretty sure that the policy is not going to persist in the future. All right. So we're pretty sure that they're going to get rid of this policy soon to preserve the trees. And we want to just get as much as we can right now. So if that's the case, then we can run this code. So we'll do model.run. So we'll say finding the optimal policy when discount is significant. And model.policy will print out a policy for us. And policy means, what should you do? Should you do wait or should you do cut, based on the current state of the forest? So let's run this. Okay, so we get 0, 1, 1. And what that means is that if the forest is in either state, middle-aged or mature, regardless, just cut that down. Cut that down right away, because you're going to want that money, that good money from the marketplace. And so we could ask questions like, should we wait or cut in the youngest state? Well, in the youngest state, let's do, Python. In the youngest state, we just do model policy 0. So it tells us just wait. But if we ask, should we wait or cut in the second youngest state, it says yes, cut that, right? And what about the oldest state? Cut that too, right? So we have a very strong discount. But now let's say, what if the policy is very likely to continue in the future? So this could be much more like 0.9 or even 0.99, let's just say. Super, super likely that things will stay the same in the future. Well, let's run our model. We'll solve for this case. And look at our policy vector here. It's 0 everywhere, meaning that no matter what state the forest is in, it's always a good idea to wait till the next year because you never know. It will once it turns into mature forest, you will get that nice $4. Okay. And so this is more or less what I had in mind for our forest management and reinforcement learning. But does anyone have any questions about this? Yeah, really curious. Wonder if you all like my Python. They're all wearing different hats. I wonder when Python's real birthday is. There must be a day of the year that Python was released. I don't know it though. All right. Well, if there's no questions about this stuff, then maybe we'll go on to the next part of our projects, our workshops, which was the linear regression. So we did mention a sizable number of people wanted to cover that topic. So let's talk about it. All right. So this is our linear regression segment, and this is a really key algorithm because it underlies so much of modern data analysis, um, and yeah, just really good to know about. A lot of people will apply this algorithm, but they won't know too much about what it actually does. So we're going to dive deep into that. But it's one of the most simple and widely used ML models, and it really models the relationship, okay, the relationship between a dependent variable and one or more independent variables. And so that is the basic idea. And it is modeled using an equation y equals mx plus b. And so in this equation, y is the dependent variable, which is what we're predicting. And x is the independent variable, which is the input into the model. And m is the slope, so that's the effect that x has on y. And then b is the y-intercept, so that's the value of y when x equals 0. Okay. And so, for example, you could make a linear regression model that predicts the salary y based on the years of experience x. So that would be an example of a linear regression application for linear regression. And linear regression, just like you might remember from our vision transformer and from our forest management case, it has a cost function. So a lot of people don't know about this cost function for linear regression, but it is the cost function mean squared error. Okay, so you would do 1 over n, sum of all n, so these are the points, sum of all points, all n points, yi minus yi hat. So yi would be the actual value of the y, the dependent variable, And then yi hat would be the predicted variable, predicted value for this point. So you would just subtract the two, square them, and add them all together. And so by adding all of those points together, you would get the mean squared error dividing by n. And our goal is to minimize this as much as possible. And so you can definitely do optimization. And the optimization algorithm, you remember with the vision transformer, we used the Adam optimizer. But in this case, we're going to actually use a different optimizer, which is gradient descent. All right, and so gradient descent is an iterative optimization algorithm, which is used to find the minimum of a function. And so you would adjust the parameters m and b, which are, remember, those slope and intercept parameters, to minimize the cost function. All right. So there are, it's similar to hiking down to the bottom of a valley. You're going to take steps that are proportional to the slope of the terrain, right? And so there's a problem to calculate the best fit line, and I'm going to give you some data. So on the x-axis, it's 1, 2, 3, 4, 5, and on the y-axis is 2, 3, 5, 4, 5. All right, so it's really, really simple data set here, but we're going to calculate the best fit line. And I'm going to do this in Excel. So I'm going to make a new Excel spreadsheet, and we'll do it together, actually. So here is our spreadsheet. It's a Google Excel spreadsheet. And we need to column X. So X will have 1, 2, 3, 4, 5, just as we said before. And then Y, I think we said, was 2, 3, 5, 4, 5. 5, 4, 5. There we go. And we want to calculate the means of X and Y. So let's actually do that. So I'm going to calculate, maybe I'll put these a little bit more central so that we can add some things to the sides. So I'm going to say mean. So the mean of X, we'll just take the average. And the mean of Y, we'll take the average of that too. A little row to just distinguish these a little bit better. And then we're going to compute the numerator and denominator for M. So this is the M numerator, okay? I'm going to put it a little, actually, I'll put it on the side. M. So the numerator for M and the denominator for M, and then M itself. So we'll say the M numerator is the sum of this. Oh, actually, we should do this in a separate column. So let's make a new column here. So we'll make X minus mean of X, Y minus mean of Y. So we have the means, right, of X and Y down here. So we can just do equals this minus this. And we'll use, we actually have to use $9 to make sure that it gets the X mean. Okay, and we'll just autofill that to get the x minus mean x. And then, so this is representing how far is this data point from the average. So the average is 3, so this data point is actually 0 away from the average, but all the other data points are either 1 or 2 away in one direction or the other. And then y minus mean y will be this minus, and this is C9, so we'll just do C $9 and autofill. So we get x minus mean x, y minus mean y. And then here we want to calculate the sum. So let's say the sum of x minus mean x times y minus mean y. So we can actually do x minus mean x times y minus mean y. So we'll just multiply these together. And we can take the sum. So the sum is 7. All right. And then this is actually what we're going to call the numerator for m. The denominator for m is going to be x minus mean x squared. So we just do this column times this column. And when we sum up, we get 10. All right. And so the slope, so m, we don't want mean, we want m. Well, maybe we'll just put it here. M is equal to this divided by, or the numerator, which is actually this column, divided by this. And so m is equal to 7. Let's highlight that so we don't lose it. And now we're going to calculate the intercept. So the intercept is actually a lot easier to calculate. It is the y mean. So let's just say intercept. It is the y mean. So y mean minus m. So there's m times x mean. So there is our b. And you can see now that we've calculated our equation. So our equation is equation. So we just say y equals this x plus don't want a formula, plus b. All right, so this is our equation. Y equals 0.7x plus 1.7. And if we change these around, we might get a different equation. But it's always solved with the same formula. And so this is the way that we do the linear regression equation. And there's actually an easier way to do this than going through and manually calculating in Excel. We can implement linear regression in code. Okay, so we're going to do a live coding session to implement this using NumPy, and we'll even do some Matplotlib so that we can see what this function looks like interactively. So let me present a new screen, which is going to be our Visual Studio Code. So here's the Visual Studio Code that we were looking at. And so what we'll do first is import NumPy as NP. and import matplotlib.pyplot as PLT. Remember, we learned a little bit about these in our data visualization track. If you want a refresher on some of this, definitely check out that track, especially part 1, which was all about matplotlib. But we'll now do the inputs for the data set. So we'll do x equals np.array, and this is how we build an array. We'll do the same for y of values in Python. So for x, remember we had 1, 2, 3, 4, 5. And then for y, we had 2, 3, 5, 4, 5. And so let's just run that. And our means, so we needed to calculate mean in our Excel example, and we need to do that for this case too. So x mean and y mean are just calculated using this built-in NumPy function, which is called np.mean, and it just computes the mean value for each of these arrays. And so, yeah, this was input the data set. We'll just write a little comment so that we have it. And then this was calculate means. And then we're going to compute the numerator and denominator for m. So numerator was np.sum, and we did the sum of x minus x mean times y minus y mean. All right, and denominator was np of the sum, and we did x minus x mean squared. And so then finally, we would be able to calculate the slope, which is m, and intercept, which is b. So to do that, we just simply take numerator divided by denominator for m. And for b, we do y mean minus m times x mean, and just save those results. And so now we can actually print out the result. So we'll just say display the result. Slope and intercept. And indeed, we get 0.7 and 1.7. So if we go back to our Excel sheet, it's exactly the same, right? So our code worked. There's a little bit of a trailing digit here, 1.700, like a million zeros, and then 2. But that's going to be a little bit different just because the computer will store those floating digits over time. Okay, so there's nothing wrong there. It's just the computer does not store perfectly these float values. But yeah, so why don't we combine all of this code into one? I'm gonna leave the import statements at the top because they do take some time, but everything else is very fast. So I'm just gonna combine all this into one code block. I don't really like running all the code blocks every time. Just run one code block. So if we run the whole thing at once, we get our slope and intercept. And we're going to expand on this actually now and plot the whole thing. So the way we can plot these two NumPy arrays of digits is using plt.scatter. So we'll use plt.scatter, and x and y are the dependent and independent variables, or I suppose in this case, x would be the independent variable, y would be the dependent variable. And then the color we have as blue. So I'll just make some nice marker blue. And then we'll say y predicted, which is this y hat we were talking about before, is m times x plus b. And We'll now do plt.plot x, y predicted, and then we'll just do show. So now you can see this is our data, there's blue dots, and the red line represents the linear regression through the data. So you can see kind of nicely how that plays out. All right, and so let's actually merge all of this into one, because I kind of like it better that way. And so everything now is one little code, and yeah, that's how it plays out. And let me go back to our slides. I'm going to copy and paste this code into the chat so that you can all see it. It's pretty small, so you can probably just, oh my goodness, it actually spanned 3 comments. Okay, in YouTube it was, wow, it was 3 comments. Okay, well, you can parse that if you want to. Let me put that in a code share, actually. I think that'll be a better way than just spamming you all with the code. Okay. There it is. Much better. Much better to actually have a little code share that you can look at. But yeah, that was how we did it. And now we can actually do some predictions with our model. So because we have the equation, we can say y equals 0.7x plus 1.7. What is the predicted value of y when x equals 7? And or when x equals 6, excuse me. And so we just substitute in 6 for x and do the math, and we get our prediction, which is 5.9. And that is sort of how the model works. And so overfitting and underfitting, I just wanted to discuss briefly. I actually discussed this already, so we won't spend too much time on it, but the idea is that you want to have enough data and enough diversity to the data so that you get an optimal fit. And overfitting could occur when your model is allowed to too specifically tune itself to that data. And underfitting is when the model has not really tuned enough to capture the nuances of the data. So we want to make this nice optimal point in the middle. All right, so let's keep going here. There's some ways to avoid overfitting in linear regression. One of them is using cross-validation. So you would split the data into training and validation sets, just like we did with our vision transformer case. Remember, linear regression is a supervised learning model, so you can do training and validation. And then regularization is another one that you can do, where you add a penalty for the complexity of the model to the cost function. So one of the most common ones is AIC for linear regression. It's the Akaike information criteria, and it represents the penalty for adding an additional variable to the linear regression model. And you want to see whether adding that new variable increased or decreased the AIC. And if it decreased it, that would be good. If it increased it, that would be bad. So you know how many variables you're able to fit in your model without causing overfitting. And so let's actually look into evaluating our model now. So let's check some of these evaluation metrics. We have the mean squared error. So mean squared error, as we mentioned, is that cost function that we were talking about earlier. let's see here. And root mean squared error is the same thing as mean squared error, but we're actually going to take the square root. And that gives us one number that is in the same units as the data itself. And then R squared is a third evaluation metric that's a little bit different than the first two. It measures how well the data points fit onto the line or curve, in this case our line, our linear regression line. So 0 would be no correlation at all, while 1 would be a perfect prediction. The line serves exactly to describe the data. So those are some common evaluation metrics, and let's actually calculate the MSE using our data set and predictions. So we can do that by using the formula of y predicted, which we already computed, and then we'll use the MSE, which is the mean, as we mentioned in the equation earlier, of y minus y predicted squared. So when we print that, it should be pretty easy to interpret. The lower it is, the better. And so, we could even print RMSE just to get it in the same units. So why don't we try that? We'll go into our code again and really try that out. So let's see here. We'll do MSE. We do mean of y minus y predicted squared. And then RMSE could be the square root of MSE. So when we print these, we get, oh my goodness, I'm bringing you everywhere, 0.38 for MSE and 0.616 for RMSE. So it means that on average, the error term on these could be about 0.6 from the line, because that would be the RMSE. And we could also do the R squared. The R squared is another possibility. So to calculate the R squared, we need to use the sum of the squared of the residuals. So we call that RSS. So it's the sum of the square of these residuals, these y minus y predicted, not the mean. Remember, before we did the mean. And then we use total sum of squares for the denominator. So that's going to be the sum of the y minus y mean. And so the R squared is 1 minus this. And when we type R squared, we should expect something pretty high, pretty close to 1. Because if you look at our data, it's quite good, a relationship. So let's see what we get. I'm really curious myself. Very high R squared. So R squared of 0.72. That indicates a very strong relationship. So we're in good business. All right, so we did actually calculate that, and now we're going to apply our knowledge to a real-world data set. And this is the Boston housing data set. And so I will send a link to this data set. Let me send it here. It's from CMU, actually. Carnegie Mellon. And I'll share my screen to show you all what it looks like raw when you actually open it. So here's the data set when you look at it raw. Looks like a lot of information. And we can check some of these variables. So CRIM, C-R-I-M, that's this per capita crime rate by town. So some of the towns in the Boston area have a reputation for being safer, and they might have a higher property value because of it. And then ZN is the proportion of the residential land that's zoned for lots over 25,000 square feet. So that means you would have really big lots that might be agricultural, or maybe really big area use, some other big area use. I'm not sure. Like some giant apartment complex could be. In this would be the proportion of non-retail business acres per town. And so that's industrial things like a big factory or warehouse. CHAS is the Charles River dummy variable. So it's just if the property value is near the river or not, if the property is near the river. And then NOx is the nitric oxides concentration. So this is interesting, right? You actually look at the pollution content over there. And RM would be the rooms per dwelling. So of course, that's really key. And then age is the proportion of owner-occupied units built prior to 1940. So how old are the people living there? Dis is the weighted distances to the 5 Boston employment centers. So how close is this to a job? RAD is the index of accessibility to radial highways. TAX is the full value property tax rate. So that's how much expensive it is to own the property in terms of tax. PT ratio is the pupils. And then B is the proportion of African Americans in the town. And then L stat would be the percentage of lower status of the population, so people who might be poorer. And then median value of an owner-occupied home would be MEDV. And so that is what we're trying to look at. That's our dependent variable right here, MEDV. And all the other ones are independent variables that we can use to predict MEDV. So why don't we open up this data set? I'm going to save it. Right-click, save as, give it some name, boston.csv. Why not? Oh, boston.txt, actually, I'm going to use. Okay. And so I'm going to use my code now. Let's open up that coding file. And we'll type import pandas as PD. And that will tell us whether or not, or how to read in the data set. PD is very commonly used to read data sets. And we can use read CSV. And we'll use downloads / boston.txt. All right. And it actually gave us an error. I suspect the reason for that error is because there's several rows at the beginning of this data set that are not actual rows. So let's see, if we just go to like 30. All right, now it seems to be working. How much can we push that? I think it should be around 20. Oh, almost. No, that was actually perfectly right. Or no, let's go down to 19 or 21. All right, there it is. And we can use header equals none. So give it no header at all. And I want to use delim white space equals true. That's going to separate all of these into columns based on the white space. So we can actually look at that. Doesn't seem like that worked actually. Let's see. Maybe we can use separator. Yeah, I think the best way to do it is to do delim white space, but it does give us this issue where the second column tends to go into the well, the first column tends to bleed into the second. Let's see. There's got to be a way for us to fix that. So let's start just by focusing on these first few variables. So we have 10 columns that we have already. So we can just name those using the columns that we had before. I wonder if we're able to say in this, if we have a very specific idea of how many columns there are, could we force the program to recognize that it needs 12 columns, let's just say. If anyone has an idea on how to do that, let me know. Okay. So I found something online to say that we should use names. So we can actually call this names. And then if we write names up here, we can then type names equals names. Let's see if that works. Oh, it still doesn't work. Dang. All right, let's see. Gonna troubleshoot this a little bit. All right, so ChatGPT is helping me out with this one because I'm a little stumped, honestly, on how to get this to work. So it looks like that helped a little bit. It actually didn't work for the first few, but let me compare to the original data set and make sure that this is working now for the others, because if it is, then we'll just keep this solution and move on. But I do want to make sure that it's working for the others too. So the second one should be 117.8, 17.8, 1870. Yeah. So let's just ignore that first one. We'll just get rid of that first one. Why not, right? We don't need that that house. That's okay. We'll leave it away. And yeah, I kind of want to make some of the visualizations from our data viz part 2 before we build our linear regression model. Just to see like what are going to be some of the most important variables here. So we can do .car to do our cross correlation, our heat map. And so I'm going to do this car Boston. And remember, if we import Seaborn, we can do sns.heatmap on this. Oh, I'm going to get rid of the annotations. That's a little too much for me. But we can see here. There are a few that are really, here's our median value. There are a few that are really important. Unfortunately, some of them you wouldn't like to see, right? You have here lower income status and households with more African Americans are very correlated, and that's mostly, obviously very bad social factor. But there are some things that I would say are quite surprisingly uncorrelated. I actually think we should let's square this, because it's actually throwing me off a little bit, because it's not 0 to 1 here. So if we do np.power, okay, that's much better. So now you can see that we're looking at r squared, not r. I kind of want to get rid of this color map too. I want to use something a little bit. What should we use? Let me check the color maps real quick. Kind of want to use Civitas, maybe. And we can use Vmax. I like to use Vmax because, this is 1. So let's actually scale it a little bit back. About 4, maybe. 4 is good. 4 looks pretty good. Maybe even a little bit smaller, honestly. Yeah, how about 0.3? That's pretty good. So age, it looks like age is super irrelevant, basically, to anything. There's almost no correlation there. Actually, now that I'm looking at it, yeah, a lot of these are still unfortunately quite correlated, but interestingly, it seems like the most correlated with the median value is actually the industrial plants. So whether there's industry nearby, and that would make sense because people probably, was it positive or negative correlation? Let's check. We can do plot. I want to do industry with median home value. Yeah, it looks like a negative correlation. So the more industry there is, the less those home values are. And it makes sense because people don't want to live in an industrial area. But why don't we choose this industrial parameter to as our predictor, since it does seem to be probably the strongest of any of these relator to median home value. And so we will use these two variables. Let's bring them. I'm going to copy them, bring them up to the top. Oh, I guess I must have gotten rid of our. Oh no, I didn't get rid of it. Here it is. This is our code for making those linear models. And I'm just going to delete these. And I'm going to say x is this and y is this. And then we can use dot values to just give the NumPy array. And so after doing that, what the heck happened? Okay, it looks like we got slope nan and intercept nan. So that means there's some nans in this data set, probably some where there's no information either way. So why don't we write a nan mask? So we're going to mask out nan values, and so the nan mask we just write nan, np is nan not x and not y. And so then we go ahead and just write x and y here and save again. And yeah, now we get our slope and intercept. So it looks like our slope is negative 0.1 and our intercept is 221. So our RMSE we can calculate is 1.8 and our R squared is 0.24. So this is more realistic R squared for an actual real world scenario. You might not get something as high as 0.74, unfortunately, but it's definitely significant because we have so many points and we're getting this R squared. So it indicates that there's a negative relationship here, a meaningful one. But yeah, I mean, going back to our data set, we know that the proportion of non-retail businesses, let's say it was 25%. So industrial, let's say in this town, industrial land is 25% of the total non-residential businesses of the total business land. So that means industrial land is 0.25. And then we can say, what is the median value of the owner-occupied homes in this town? Remember, this is in units of $1,000. So we're just going to do M times industrial land plus B. And then I'm just going to print out median home value, but I'm going to print it out times 1,000 because I want to see the actual home value. Now remember, this is a data set from 1978, so it's going to be a little bit low on the low end, but there it is. So it's saying that it was about $21,000. Now, if you told anyone that they could buy a house in Boston for $21,000 now, you would definitely want to do that because now the average one is probably almost $1 million. But yeah, that sort of caps it for our linear regression example. So yeah, does anybody have any questions about what we did today? So we talked a little bit about reinforcement learning, which is forest management. How do you optimize in this scenario? And then we talked about this linear regression example, where we dive deep into the fundamentals of linear regression, and it's machine learning algorithm like anything else. It's minimizing the cost function, just like Vision Transformer did in our first portion of machine learning. So yeah, I hope you all enjoyed that, and Thanks for sticking tuned.